Good morning. My name is Chandani Thakur. I'm a member of the Harker Wisdom Club, and I'll be presenting our first keynote speaker. Dr. James McClintock, a devoted researcher and professor of polar and marine biology at the University of Alabama at Birmingham, explores Antarctic marine chemical ecology, specifically invertebrate nutrition and reproduction. After earning his bachelor's from UC Santa Cruz and doctoral degree from the University of South Florida, he completed a postdoctoral fellowship for the National Science Foundation, which later funded his 14 Antarctic research expeditions. During the past 25 years, McClintock has published over 235 works, partly centered around the impacts of climate change. Featured in articles and broadcasts including National Geographic, CNN, and Scientific American magazine, his work has resulted in several awards, a fellowship with the American Association for the Advancement of Science, and countless more recognitions for both teaching and research. His world-renowned book, Lost in Antarctica: Adventures in a Disappearing Land, has accumulated overwhelming acclaim for his extensive research and findings. Throughout the years, his studies of Antarctic algae and invertebrates have immensely contributed to knowledge on rapid climate change. This summer, Dr. McClintock will be coordinating with Harker students in preparation for their trip to the Arctic and helping them conduct research projects about climate change. Today, we are honored to welcome Dr. James McClintock as he presents us with an opportunity to explore the Antarctic and see a world that is so foreign to us, yet so highly impacted by our own actions.
Well, thank you for that very nice introduction. It's an honor to be here at the Harker School and part of this annual event. I've been working in Antarctica for almost 30 years, and I have to tell you that the first time that I put on a dry suit and I slipped into water that was minus 1.8 degrees centigrade and dropped below the ice, I was stunned. I didn't realize that the seafloors of Antarctica were one of the richest marine ecosystems on our planet. Really, if you look at the amount of marine life on the seafloor of Antarctica, it's similar to the Great Barrier Reefs of Australia. And I fell in love with it. I wanted to understand how these animals lived in this very rigorous environment, how this ecosystem was essentially structured, and what controlled the variables that went into making it what it is. And I've spent a career doing that. So the first maybe 12 years of my career in Antarctica, I worked at McMurdo Station, which is below New Zealand. And then I was fortunate enough 15 years ago to be invited to move over to Palmer Station on the Antarctic Peninsula. Now, it turned out that Palmer Station, on this 1,000-mile peninsula below South America, is undergoing very rapid climate change. And so I just happened to be sort of at the right place to see it personally. And that's really what I want to talk about today. So I'm going to talk about the ecological impacts of climate change in this just stunningly beautiful area of our planet, the Antarctic Peninsula. So if you went back to a National Geographic issue in 2006, the orange areas that show warming on our planet were generally focused up here on the Arctic, where the group of Harker students will be heading this summer. But down here on the Antarctic Peninsula, you can also see an area of warming. And even in as recent as 2006, the rest of Antarctica wasn't really considered to be warming much. But then look at the cover of Nature magazine in 2009. This is essentially showing that not only is the peninsula of Antarctica warming, but the western sheet of Antarctica, the western portion of the continent, is also warming. Now you have to remember that this is a very large continent. This is China and India combined in size, Antarctica. As recently as 2013, scientists have discovered that not only is the peninsula and the western side of Antarctica showing signs of warming, but now we've got areas along the eastern side of Antarctica. This is the ice shelf melting, and it's being caused by the Antarctic Circumpolar Current, the world's largest current that circles the continent. And as that warms, even the eastern side is being impacted. Well, how much warming are we talking about? Well, here is where I'm working, below South America, right here on the Antarctic Peninsula. The little station run by our government, the National Science Foundation, is located here on Anvers Island. It's a small station of about 45 people. And very fortunate for us, 20 miles away is a Ukrainian station. Used to be a British station, but the Brits decided to sell it to the Ukrainians for £1. And they've been taking air temperatures at this station for 60 years. And if you look at the air temperatures over this period here from 45 to 2005, a period of about 60 years, you can see that it's been increasing in temperature about 1 degree centigrade per decade, or a total of about 10 degrees Fahrenheit. This is remarkable. This is truly remarkable. This makes this Antarctic peninsula warming at a rate that's similar or perhaps even slightly greater than the Arctic. So what does this mean? Well, it means, for one thing, that when I first arrived at the station 15 years ago, about once a week, you would hear a huge crashing sound outside the station. You'd run down the hall, you'd throw open the door and look into Hero Inlet, and you would watch a huge section of the Mar Glacier calve break off into the bay. It was a big deal. Now when I go to Palmer, I would say that probably 4 or 5 times a day I hear this noise. I don't get up from my computer anymore and run down the hall. This has become very common. And in fact, 87% of the glaciers along the western Antarctic Peninsula are retreating. Now we have harder data than anecdotes about running down halls. This is actually the science tech who works at the station, and once a year their job is to put on a backpack. It's got a little GPS device in the backpack. He hikes the leading edge of the glacier, he or she. And what they do is essentially they're talking to a satellite above with a very great accuracy. I think it's within a few centimeters. And you can then map the progression of the retreat of the glacier. So back here is Palmer Station, and my colleagues Chuck and Maggie Amsler, who came down in the late 60s, said you could almost open the door of the station and step onto the glacier. And now you know what? It's a half a kilometer hike to get from the station to the edge of the glacier. So it's a very dramatic recession. Here you can see it in an aerial photograph. Here's Palmer Station out here on the peninsula. Here's where the edge of the glacier was in 1975, and here it is recently in 2013. And you know what? This was thought to be a point of land, and when the glacier pulled back, it was an island. So it's now named for Chuck and Maggie Amsler. All right, I also want to show you that the glaciers are not only retreating, but they're thinning. Can you imagine an instrument so sensitive that a satellite can essentially measure the thickness of glaciers around the continent? So the areas of red are areas of glacial thinning, and it sort of reinforces what I've been saying. The western part of the continent is definitely warming, the peninsula, but not so much on the eastern side, except for under the ice sheets, as I talked about, from the Antarctic circumpolar current. And here's Greenland, which you've probably heard, is also undergoing a lot of glacial thinning and warming. This was in the news very recently, and it was quite concerning to scientists who work in Antarctica on ice dynamics. Essentially what it's showing is there's a glacier here on the western side of Antarctica that's showing signs of rapid retreat. And the concern is that the western Antarctic ice sheet, remember Antarctica is covered with 2 to 3 miles thick ice. It's 80% of our drinking water in the world is locked up in the ice sheet. Essentially, what happens is that this glacier area here is where the western Antarctic ice sheet flows. You have to remember this ice sheet is like flowing into the ocean very slowly. The concern is if this glacier breaks out, the rate of flow will be greatly accelerated, and this is going to have an influence on things like sea level rise. There's some other features of the ice that are changing. Not just the glaciers, these are ice sheets. Now, ice sheets are about 200 feet thick. They're not on land. They're connected to the shore. And these are the sites of some major ice sheet breakouts over the last 30 years. And I want to highlight 2 of them for you. The Larson Ice Shelf B up here, and then we're going to go down and look at the Wilkins Ice Shelf. So the Larson B Ice Shelf is up here on the eastern side, and in 2002, a satellite image of the Larson B showed these striations forming in the ice sheet. They came back a month later, somewhat concerned about what was going on, and discovered that the entire Larson B ice shelf was in the process of disintegrating, and in fact, On March 5th in 2002, essentially the whole Larson B ice shelf was headed out to sea. Now, this is a piece of real estate about 5,700 square kilometers in size. So this is about the size of the state of Rhode Island that has broken out in here. More recently, you may have heard in the news that the Wilkins ice shelf down at the base of the Western Peninsula has broken up. As I stand here, it has not quite gone out to sea. It's sort of dangling from an island, but it will eventually. And when the Wilkins ice shelf is gone, we've lost a piece of real estate about the size of Connecticut, about 29,000 square kilometers. So these are major ice sheet breakouts. The good news is that when ice sheets break out and melt, they do not contribute to sea level rise. And that's the same concept as having a glass of ice water. When the ice melts in that glass, the water doesn't come over the top. So the physics is in our favor. What's unfortunate about losing these massive pieces of ice is that they are in fact blocking or barriers to the flow of ice off the land and towards the sea. So scientists have discovered that the rate of flow of this ice is accelerated about 3 or 4 times when you lose these ice sheets that were formerly barriers. And this does contribute to sea level rise. When the ice comes from the land into the sea, it has an impact. And in fact, the International Panel for Climate Change recently incorporated the amount of ice coming from the Antarctic continent and Greenland into their models for sea level rise. And it's around about, I think it's about 0.3 to a meter of sea level rise expected by the end of the century when you take into consideration Antarctica and Greenland and all the other former parameters. So what does this mean to a marine ecologist like me? Okay, it's sort of a backdrop on the ice features of Antarctica and what's happening on the peninsula. How are the marine communities responding to these very rapid changes? Well, probably the most poignant story, it comes from the Adelie penguin. These are the little penguins that look a little bit like Charlie Chaplin. They got those black and white suits on. And this guy right here, his name is Bill Fraser, is a good friend of mine. Bill came down here to the Antarctic Peninsula in the mid-'70s when he was a graduate student. So, maybe in his early 20s. He's been coming back every year since. And Bill has been studying the populations of Adelie penguins near the station. When he showed up here as a grad student, there were 15,000 pairs of Adelie penguins. Bill can tell you everything about these penguins. He can tell you whose uncle is related to whose aunt and how many eggs they laid in 1984. It is just phenomenal. It's one of the most amazing databases we have on any animal on the planet. Well, what Bill has found is that the Adelie penguin, this one here, in the purple line, here's the 15,000 breeding pairs when he showed up as a grad student, has plummeted down to about 1,500 pairs. He told me this just about, within the last year. So about a 90% decrease in Adelie penguins. The Gentoo penguin and the chinstrap penguin have shown up. Well, this is interesting. They shouldn't be here. These are sub-Antarctic species that are moving down as it's warming. So here you have the Gentoo showing up in the 90s. There's about 1,000 breeding pairs. Not a huge number, but they're very successful. And the chinstrap penguin showed up in the 70s and never has really gotten more than about 300 breeding pairs. But here we have 2 penguins who have shown up. What's happening to those Adelie penguins? Why are they disappearing? Well, Bill has several ideas. One of them has to do with something that's a little bit ironic. As it's warming on the peninsula, the air is becoming more humid. As the air is becoming more humid, it's snowing more and later than it ever has before. So you're getting these unseasonable snow events. So what happens is the Adelie penguins are genetically hardwired to show up at the same time every year and lay their eggs. They come in, they lay their eggs, and then all of a sudden, they have these very unusual snowstorms that bury them in snow. And sadly, what happens when the snow melts is those eggs drown, and you can lose an entire generation of penguins from one of these snow events. The other thing that Bill believes is important in the Adelie penguin story is the annual sea ice. Now, we haven't talked about annual sea ice. That's very thin. It's about 3 or 4 feet deep. It doubles the size of Antarctica every winter, and then it breaks up and goes out to sea. So along the Antarctic Peninsula, where it is warming so rapidly, the annual sea ice has retreated about 40%. And that's both in terms of how long it's there and how far offshore. Well, the Adelie penguin's ecology is very tightly in tune with the annual sea ice. They actually use the annual sea ice as a platform to toboggan across on the surface and get out to the edge of the sea ice where they get the krill, the little shrimp that are so important in Antarctic food webs. And there's big schools of krill off the edge of the ice, fair distance offshore. So Bill thinks what's happening now is these penguins are having to leave the ice and swim out to these big krill populations using very critical energy that they need to essentially raise their young. And that's having its toll on the penguin. The other thing that's happening is krill. These little quintessentially important organisms that feed whales and seals and penguins and fish in Antarctica, it turns out that we've discovered in the last 20 years that when they're teenagers, krill live under the annual sea ice. And you can kind of see this big ball of krill under the ice here, and they're feeding on little plant cells called diatoms under the ice. Well, guess what? As that annual sea ice is disappearing, so are the krill. And that's a very important part of the sort of the food web scenario in Antarctica. So that's another pressure on the Adelie penguin. Now, if you think about it, any of the animals along the peninsula or in Antarctica that use the annual sea ice every year as part of their life history or ecology could be affected. One of them is the Weddell seal. Now, the good news is I think the Weddell seal will just follow the ice edge. I don't think as it retreats. I don't think they're going to disappear like the penguins. But I got to tell you this really neat story about Weddell seals. And it has to do with their teeth. The female Weddell seal has ice-chipping teeth. And what she does when she's pregnant is she swims up under the annual sea ice. She looks for a weak spot in that ice and begins to chip with her teeth until she gets a little tiny breathing hole, and then she can take her time and continue to chip away at that little hole until it's large enough that she can slide right up through the hole and give birth on the ice, completely separated from predators like the killer whales or the leopard seals that are prowling along the ice edge. They cannot get to her. And it's all because of these ice-chipping teeth. It's a wonderful adaptation. Well, this is a seal that you probably don't want to see if you happen to be scuba diving in Antarctica like I do. This is the leopard seal. Leopard seals are about 10 feet long, about 1,200 pounds, and very, very territorial. When we see a leopard seal and we're diving, we have a special little device we drop into the water. There is a siren that goes off underwater when I flip the switch. It tells the divers below that there is a leopard seal that's been sighted, and they need to come together back to back and come up to the surface as quickly as possible and get into the boat, because leopard seals are very, very aggressive, and they will swim by you underwater, getting closer and closer, and we just don't want to take any chances. Now, leopard seals also use the sea ice. They kind of use pieces of sea ice floating around to digest a meal. Nobody knows what's going to happen when the sea ice is gone. Are the leopard seals going to go up on shore to rest, or are they going to follow the ice as it retreats? That will be interesting. What about the little things? What about the tiny little plankton that live in the water? Are they being impacted by these very rapid changes? Well, we're very fortunate that the National Science Foundation has had for the past 35 years a program in place at Palmer Station that looks at plankton. And the director of that program is smiling at you right here. His name is Hugh Ducklow. Hugh is a Harvard graduate who is the director of the National Science Foundation's long-term ecological research program at Palmer. So he's got a whole bunch of scientists and ships, and they have been studying the plankton along the coast here for a very long time. And I just want to show you a recent study that they have on this that appeared in the journal Science. That's sort of the most prestigious journal that you could publish in. So here's what they did. These are transect lines where the ship went up and down, taking samples of plankton all up and down the Antarctic Peninsula. And they kind of divided the study up into an area towards the tip of the peninsula and towards the base. So let me summarize what they found in this cartoon for you. Overall, they found that this part of Antarctica is going from a cold, dry, polar environment to a warm, humid, sub-Antarctic type of climate. And if you look at the very tip of the peninsula, here's the story. The weather's changing. The skies have gotten cloudier. There's less light. The winds are blowing harder. So this churns up the ocean surface. And what that does is it pushes the plankton, the little photosynthetic plant cells, deeper. They're having a hard time photosynthesizing deeper. And you're losing the phytoplankton. You have less phytoplankton, particularly these plankton called diatoms. Well, diatoms are the favorite food of krill. So part of the reason the krill are having trouble up here is there's less food for them to eat. At the same time, salps have moved in. Salps are not good news. Salps are oceanic little invertebrates that look like a walnut made out of jelly. And unfortunately, salps are not nearly as nutritious a food resource as krill are. So essentially what you're doing is you're taking krill, steak, and you're replacing it with salps, lettuce, okay? And that's having an impact. Further down the peninsula, things haven't changed as much, but Hugh Ducklow thinks that eventually it will look very much like the northern part of the peninsula. Well, what other things might happen as it's warming? Well, one thing that is a lot of people don't realize about Antarctica is there are forests in Antarctica. All you have to do to find a forest in Antarctica is put on your scuba gear and dive into the water in front of Palmer Station, and you will be literally swimming through a forest of seaweeds. They'll tower over your heads. It'll be a lot like the kelp forest that you see here in California. What's going to happen to these forests as it warms? Well, probably they're going to do very well because the sea ice is disappearing. The sea ice blocks the light. So now these forests are going to have plenty more light. They're probably going to grow deeper than they have. They're probably going to extend their range further south. But we also know from our chemical studies of these algae, these seaweeds, that they have toxic chemicals in their tissue that keep them protected from a soup of little crustaceans that they live in. So how is this additional energy coming from additional light going to influence their production of these toxic chemicals? Could it alter who eats who in this scenario? We don't know. What about marine invertebrate larvae, the little babies produced by starfish and sponges and soft corals and all those organisms? This, believe it or not, is a baby starfish. This little larval organism will spend 4 months developing in the plankton of Antarctica and then metamorphose into a little starfish. It's almost as dramatic as a cocoon to a butterfly. So here you have these little larvae, and I know from some of the work that I've been involved in that if you bring these larvae into the lab and you warm them just a little bit, 2 degrees, let's say, instead of taking 3 or 4 months to develop, they develop in 2 or 3 weeks. They're very, very sensitive to temperature. And it's not surprising. This system has been sitting at this very stable temperature for millions of years. So they're very responsive to these changes. Well, maybe that's a good thing. If they develop in 2 or 3 weeks, that means that they're not out there vulnerable to predators that could eat them. But the other problem that I think might arise is a lot of these larvae are feeding on plankton. And the plankton occurs in these big blooms. We call them plankton blooms. And what happens if their timing is off? Now they're developing a little too fast before the plankton bloom. It's kind of like showing up at the cafeteria and the door's locked. Are they going to be offset from their food resources? And this is just to show you that Antarctic embryos, these here, compared to temperate and tropical species, are so temperature sensitive. If you change the temperature just a tiny little bit, it has a big effect on their rate of development. All right, let me talk a little bit more about range extensions. I've already hinted that there are 2 species on the peninsula that weren't there before that have extended their range. That was the Gentoo penguin and the chinstrap penguin. What about these guys? elephant seals. 15 years ago, the chances of my opening the door at Palmer Station and tripping over a 2,000-pound male bull elephant seal at the base of the stairs was very low. And now the elephant seals have arrived. They will be 10, 15 big elephant seals laying around the station. These are subantarctic species that, as it's warming, are moving down and into formerly colder areas and establishing breeding colonies. There is now a breeding colony near us. You can hear the pups barking in the distance. And the Antarctic fur seal has also begun to show up, another subantarctic species moving in. And they haven't established breeding colonies yet, but I suspect they will be. Probably the most dramatic example I can give you of a range extension, and dare I say invasion, has to do with an invertebrate, okay? And I'm just going to set the stage for you. Imagine Antarctica 35 million years ago, separated from South America, the last continent it was connected to in Gondwanaland. When Antarctica separated from South America, it allowed the establishment of the world's largest current, the Antarctic Circumpolar Current. That essentially locked Antarctica into an icebox. Some of the species survived, many did not, and there's some very conspicuous things not in Antarctica. For example, there are no sharks in Antarctica. There are no fish with crushing jaws. There's 250 species of fish in Antarctica. They are wimps. They feed on tiny little crustaceans. If any of you have ever put on a mask and a snorkel and gone into the South Pacific or the Caribbean, you may have heard parrotfish crunching away eating corals. You don't find anything like that in Antarctica. There is no fish with crushing jaws. There is nothing in Antarctica with a claw. There are no crabs. There are no lobsters. So essentially you have an ecosystem that for 30-odd million years has evolved in the absence of crushing predators. If I was to hand somebody in this audience an Antarctic clam, you could take your 2 fingers and crush the shell very easily. The shells of Antarctic marine invertebrates are wafer thin, okay? They just haven't had to worry about crushing predators. So you can imagine the surprise of my colleague, Sven Thaci, who on January 25th, 2007, was sitting in a ship 1,100 meters above where this picture was taken by a submarine. He was stunned. For the first time in history, he had discovered king crabs moving up the Antarctic slope towards Antarctica. This really was very, very unusual. So the theory goes that as the deep water surrounding Antarctica is beginning to warm, and we know it is, that crabs, which have lived in the deep sea around Antarctica for millions of years and have been held at bay by low temperature, they cannot regulate magnesium in their blood at low temperature. They act like they're drunk. They stumble around, they can't feed at low temperature. The theory goes that that physiological barrier, the curtain, is being opened. And for the first time, crabs are beginning to move up the slope and into Antarctica. And at the same time I began to work on this, and with a grant from the National Science Foundation, another group of scientists discovered millions of these crabs living in a deep canyon within sight of Palmer Station. And now I have a colleague, Rich Aronson, who he and I have funds that take this ship down to Antarctica every year, and we drag a submarine that we lease from Woods Hole up the Antarctic slope and onto the Antarctic shelf in kilometer-long transects. And we've discovered that the crabs are there. They're moving up the slope. They haven't gotten to the shelf yet, but we suspect they will. And when they do, they could have a very profound effect on the ecology of this ecosystem. And then finally, I want to mention something about ocean acidification, because it's unique in Antarctica. Now, you may or may not have heard much about ocean acidification, but in addition to climate warming, greenhouse gases are also responsible for ocean acidification. A third of the CO2 that goes into the atmosphere ends up in the ocean. And there's a series of chemical reactions that occur that make that ocean water more acidic and makes it more difficult for animals to build shells. Antarctica is a very ripe place to study ocean acidification, and that's because it's very, very cold water, and carbon dioxide is more soluble at low temperature. It's also because I've already told you, these animals don't have much of a shell to begin with. If their shell dissolves, they have a big problem. So I can tell you right now, you can go to the Southern Ocean and you can dip your net into the water and collect these beautiful shelled butterflies called pteropods. They're very tiny. You have to look at them almost under a microscope to see them. But they're as abundant as the stars in our universe. They are absolutely everywhere. If you bring one into the lab now, there are places in the Southern Ocean where you can actually begin to see that the shell has eroded from ocean acidification because of this particular phenomena. So this is just amazing. This is not in the future. This is now. And I wanted to tell you this really neat story because maybe it's possible ocean acidification could affect relationships between how organisms interact. And I wanted to relate it to this wonderful story where, so one day I was out on the sea ice and I looked down into a dive hole and I saw this little shrimp-like animal called an amphipod swim by with a little orange ball on its back. What was going on? So I brought it in the lab and I took off the little orange ball, and it was a sea butterfly. It was kind of a sea butterfly that doesn't have a shell. And I put out nets around the area and I caught hundreds and hundreds of these little shrimp-like animals, and 75% of them were carrying a sea butterfly on their back. And if you took the sea butterfly off the back, it would open its wings and it would fly away. What was going on? So of course, being a scientist, I collected some and brought them in the lab, and I took the sea butterflies off the backs of the little shrimp and offered them to a fish, and the fish ate them every single time. And then I left the little butterfly on the back, and I offered a whole bunch of these little butterfly-carrying shrimp to the fish. They'd take them in the mouth, spit, kind of taste them, and then poof, spit them out. And away would go the little shrimp, happily. So I had discovered with another colleague that one species is abducting another species in order to defend itself. And it was very, very interesting. And it sort of tells you how intricate these relationships can be in the ocean and how much we have to discover yet. All right, so this is a list of what I've talked about. What's happening where it's warming on the peninsula so dramatically is the glacial recession, the ice sheet breakups, the pack ice. Species associated with that pack ice are being impacted. The phytoplankton is changing. We may have community effects on these forests, larval development, on extension of species like elephant and fur seal ranges, maybe even king crabs, and now we have ocean acidification. So it's really a very dramatic impact. And I just wanted to mention one more thing about ocean acidification for all of you students in here, because this is two of my student projects, and they're working on ocean acidification here at Palmer Station and studying how ocean acidification affects limpets, these little snails here, and also these little coral and algae that grow on the shells of the limpets. So we've gone from a community that looks like this. It's probably looked like this for millennia. We've had the annual sea ice. The Adelie penguin populations are very abundant. We have lots of krill in the water. We've got these seafloor invertebrates and these forests, and this is all being fed by this rich Antarctic circumpolar current. And here's where we're headed, probably by mid-century, I would guess. The sea ice is going to be gone. The Adelies will be gone. The gentoo and the chinstrap will have moved in larger numbers. The krill will largely be gone, replaced with these little lettuce organisms I call salps. And maybe we'll have king crabs move into this ecosystem, altering it, and the forests will be somewhat larger and deeper, and we'll have this again all being fed by these very nutrient-rich Antarctic circumpolar waters. So this is a very dramatic change. Communities always change, but over a few decades, this is a profound change in an ecosystem over this time period. All right, so why should we care? Antarctica is a long way away. These communities, you might think, don't really affect our everyday lives. I just want to give you one sort of concrete example that relates to my own research in chemical ecology. And that has to do with the fact that when we do our studies of chemicals that are involved in relationships between organisms in this community, we also take all the chemicals that we find and we ship them off to the National Cancer Institute, to the Cystic Fibrosis Research Institute at my university, to a number of different pharmaceutical companies to see if there's any potential in these Antarctic compounds fighting human disease. And in fact, when we're diving under the ice, whether it was at McMurdo or diving out of Zodiacs over at Palmer Station, and we're collecting these marine organisms, extracting their chemicals, we're always hopeful that there might be some good news in that regard. And I work with a fellow named Bill Baker, who's a chemist, and he and the rest of our group have found some pretty neat things, and I just want to share two of them with you real quickly. One is a compound that we named pomerolide. One of the really cool things is when you discover a new chemical, you get to name it. So we named it after Palmer Station, pomerolide. And when pomerolide, which comes from these orange ball-like organisms called tunicates, was sent off to the National Cancer Institute, they tested it against 25 different lines of cancer: breast cancer, prostate cancer, you name it. And actually, the National Cancer Institute called us up and said, we're really excited about this compound because it's very, very active, but only against one kind of cancer. It's very active against melanoma, a deadly skin cancer. Can we work on it? Yes, you can work on it. So the National Cancer Institute worked on it, and eventually they figured out how it works. They figured out that you can make it in the lab. They figured out a bunch of stuff that means that now some pharmaceutical companies are potentially interested in developing it into a drug. The other compound that was very exciting is from an algae, a seaweed in Antarctica, and it's a protein that's very, very active against the H1N1 flu virus. So my point here is that this is an amazing resource. These organisms in Antarctica have evolved for 30 to 40 million years, and they have a huge library of all sorts of compounds that could be important. What a shame it would be to squander that. All right, so I do a lot of talks on climate change, and I used to get asked this question: is the climate really warming? I have not been asked this question probably in 5 years. You can go online, you can find plenty of evidence for global warming. I want to share with you the irrefutable evidence that convinced me that, in fact, the planet is warming. Nobody in their right mind can take these data to task. This is absolute confirming evidence. All right. So now, the question has turned, what I get asked now when I lecture on climate warming is, do we have anything to do with this? Or is this just a natural cycle that our planet goes through? And I want to share with you what convinced me. You have to make up your minds about this. But this is what convinced me as a scientist. And conveniently, this is from Antarctica. How cool is that? So what you're looking at here is really very simple. You're looking at an ice core. You're looking at an ice core that went down through the Antarctic ice sheets. It went down 3,600 meters through the ice. And trapped in the ice are little air bubbles. And inside those air bubbles are historical signatures of what the atmosphere of our planet contained in terms of carbon dioxide. That's what this red line here is. And then scientists can take the oxygen isotope ratio from within that little bubble, and they can also calculate temperature, which is the blue line. But I want you to look at the red line. It goes back over 430,000 years, and this has now been extended back to 1 million with the same result. This black line that I've drawn right here shows that you get these 100,000-year cycles of carbon dioxide in our atmosphere, but it's never gone over 300 parts per million over the last 430,000 years. But look what happens over here when we get to the Industrial Revolution, and I've blown this up. This red line just skyrockets. In fact, probably we should update this, but I can tell you that in 2014, it hit 400 parts per million. So that is what? That's a 25% increase in CO2, a very well-established greenhouse gas, in our atmosphere since the Industrial Revolution. To me, that's very strong evidence that, in fact, we're having a significant role in warming. Oh, and I know you were curious about these 100,000-year cycles of carbon dioxide. And those are being driven by a 100,000-year cycle. It's an elliptical orbit of the Earth around the sun. It's called the Milankovitch cycle, and that's what scientists believe drives that 100,000-year cycle. So, gloom and doom. But that's not my way of looking at all this. And I can't leave you in a negative context with this. So I'm going to tell you a wonderful story to end my talk, okay? I'm going to tell you about the story that took place and started 20 miles from where I work at Palmer Station. At that same station that I talked about earlier, only at this time the station was British, and it was 1984. And there were two technicians sitting at their desk at the station, and they emailed back to their boss in Great Britain some data, and he wrote back and he said, "I don't believe this, I just don't believe this." And they said, "Well, this is what we found." And they said, well, the boss said, "I'm going to get you a new spectrophotometer. You're going back to the station for another season next year. You're going to retake these measurements." And they did. And they got the same result. So what happened is probably the most important paper of the 20th century was published in Nature, reporting a massive hole in our atmospheric ozone that completely opened up Antarctica, that actually extended periodically over New Zealand, this massive hole in UV protectant ozone. In fact, 8 years ago when I lived in New Zealand on a sabbatical with my family, I'd have my coffee in the morning with the paper and I'd open up the weather section. And in the weather section was what strength of sunscreen you were to put on that day in New Zealand as a function of the hole in the ozone. Was it over New Zealand that day? Amazing. And New Zealand has the highest rates of skin cancer of any continent in the world. So what was so amazing to me was not so much this discovery, but that within 2 years, in 1987, over 20 countries sat down around a table in Montreal, Canada, and agreed to sign the Montreal Protocol. Okay? The Montreal Protocol prohibited the use of chlorofluorocarbons, which were determined to be the destroying agent of ozone. Those are things that are commonly used in refrigerants, and now they've been replaced with chemicals that don't destroy the ozone. So it's really a phenomenal kind of discovery. Today, there are 193 countries that are signatories to the Montreal Protocol. It's probably the most successful global treaty of all time. And it's worked. I can tell you because Susan Solomon, who's the woman who discovered the chemical reaction that destroys ozone, she's at MIT, was with me a few years ago at my university when she came to speak. And when I drove her to the airport, I said, "Susan, what's going on with the hole in the ozone? You're right in the middle of all this." And she said, "You know, the news is good. The news is that the hole in the ozone has stopped growing, and now we believe it's possible that by the end of the century or earlier, it's going to close. It's going to be gone." So it's really a remarkable, positive story. All right, so that's my vision of hope for the future, that we can work on this problem just as we did with something like the hole in the ozone, which affected us on a global scale. But before I leave you, I have to tell you a few sort of interesting little stories that are sidelines to publishing my first book for a popular audience. And that's called Lost Antarctica. So one of the things that I didn't realize when I published the book is that one of the world's most famous scientists, E.O. Wilson, would get a hold of me, and I have to admit, I'd known him before. He's kind of a friend of mine. He put me on his board of advisors. And I was very humbled because everybody on the board seemed to have a Nobel Prize, which I don't. And then I got a phone call from the director of the E.O. Wilson Foundation, the Biodiversity Foundation, and she said to me, her name is Paula Ehrlich, she said, "We want to make a 3-minute video out of one of the chapters of your book, the story of the Adelie penguin. And we want it's going to go into the zoos and the aquariums across the country. And we really like the prose." And I said, "Well, I would be honored to read for this little video piece my prose." And she said, No. We'll have Harrison do it." And I said, "Harrison? Who are you talking about?" "Harrison who?" well, he's on the board with you. I said, I had no idea. So Harrison Ford read from my book, and they did this wonderful little 3-minute video. You can go online, you can go to YouTube, and you can watch Ghost Rookeries, and you will hear this wonderful Star Wars actor reading from my book. The other thing that happened from the book, which I never would have anticipated, was one day I was minding my own business in Antarctica. I was the chief scientist at the station, and the station leader came to me and said, Dr. McClintock, we've got a visitor tomorrow. Would you be their host for the day? And I said, sure. He said, well, I can't tell you who it is. It's security. I said, you got to be kidding. We're in Antarctica. You can't tell me? So the next morning, a yacht pulled up, and there was Bill Gates and his father, Bill Sr., and his son, Rory, and his stepmother. And so I spent the whole day with him. Had lunch, showed them the labs, talked about all the science. Bill Gates was very interested in climate change and its impacts on Antarctica, and told me all about his work in Africa and medicine. And, you know, what was so amazing was after lunch, I took him and his father up to this special room at the lab where we have a big screen, and there's 2 big chairs in the front of the room, and I was going to show them the National Science Foundation video that talks about all the neat things that we as a country are doing in Antarctica. So imagine Bill and his father sitting there in the 2 chairs, and I'm sitting behind them. In comes the IT guy. He cannot get Microsoft to boot up. 2 minutes, at least. Do you know how long 2 minutes is in front of Bill Gates and his father when you can't get Microsoft to boot up? So anyway, it occurred to me that you would be especially appreciative of that Microsoft moment. And finally, I will tell you, as many of you know, that I've been involved with Abercrombie and Kent taking people to Antarctica. And these are not scientists. This is the general public. When I was approached 8 years to do these cruises, to be honest, I was a little concerned as a scientist working in Antarctica, taking tourists down and showing them. But you know, it's been wonderful. And I've been taking people down now. I guess I've taken, I don't know how many, but quite a few. And then I was involved last summer in the Arctic, and my research associate will be taking some of your students up to the Arctic. These are amazing experiences. These are experiences that change you. I mean, really, you come back as become sort of an ambassador to Antarctica or the Arctic. And so I really believe it's a very valuable kind of experience and something that scientists should be involved in. I get to go take people and show them my station where I work and what their tax dollars are doing. And I think that's a very positive thing. And with that, I will be happy to take any questions. Thank you so much. Does anybody have any questions for me? Yes.
Do you find there's enough funding, either from the U.S. or private sources, to do the kind of science that needs to be done? And are there scientists who are working with them?
Good question. Is there enough funding and person power to do the kind of climate science we need to do in Antarctica? And I think generally the answer to that is yes. The competition as a scientist to work in Antarctica is heavy. There are certainly fundable proposals that don't quite make the cut, which I always find a little discouraging. But the other thing that you have to think about in Antarctica is that these stations can only handle so many scientists at a time. So I think we're maxing out the stations in terms of their utility. I will tell you that there has been a very significant interest in the impacts of climate change on the Antarctic systems, everything from people that are doing atmospheric chemistry to marine scientists like myself. The numbers of proposals that have a climate change focus has skyrocketed because Antarctica and the Arctic are sort of quintessentially important in understanding what's going on with climate change. It's where changes happen first. Organisms are more sensitive in those environments to even the smallest changes. So we learn stories there that are applicable to temperate and eventually even to tropical systems. So is there room for more resources? There always is. Are we doing a great job in climate science? I believe we are. Yeah. Okay.
So, does this still work?
You going?
Okay. So we'll be using Slido questions. So if you want to ask any questions, remember to go to slido.com with the hashtag symposium so that you can submit yours. And if there are any questions that you see that you would like to hear him answer, then you can upvote them. So the most popular question right now is, have you hugged a penguin before?
I would not be standing here. I would be doing 3 years in jail right now. So the Antarctic Treaty, which is wonderful, it protects Antarctica from any sort of military or industrial exploitation. It's a science laboratory for the world. It's wonderful. Protects Antarctica. So you're not allowed to get within 15 feet of a penguin, according to the Antarctic Treaty. The problem is penguins don't read. And so when you go to shore, it's not uncommon that the penguins will come literally right up to you. They'll be standing within a foot, staring up at you. And so, you don't reach out and hug them because that would scare them. But you can see them very, very close. It's wonderful.
So since no country or organization owns Antarctica, how do scientists interact or compete with other international scientists?
So the Antarctic scientists have a program called SCAR, the Scientific Commission on Antarctic Research, that brings all the scientists from all the different countries working there together every several years. There's collaborations going on all the time between different countries. So it is a very collaborative environment. And I love the part about nobody owns Antarctica, but there are countries that think they do. If you look at a map of Antarctica, you'll see it's carved up like pieces of the pie. We do not do that in our country. We just put ourselves right smack dab in the middle. We have the pole station, right? But in Argentina and Chile, they are serious. In fact, they used to have a program in Argentina where they would pay young couples to go down to Antarctica to give birth, because one of the ways that you claim sovereignty to land is to give birth upon it. So that's how serious some countries are.
So what are some of the data collecting methods you use when researching climate change?
Some of the dive collecting methods we use. What's that the question?
Data collecting.
Oh, data collection. Okay. Oh, goodness. We're all over the place. We're collecting data in the field. We have experiments that we deploy out onto the seafloor. So we have these special white slates that we can write on underwater as we're recording information. The latest thing is to have, what are these little cameras called that the guy made millions of dollars on the front of his? GoPros, yes. So now scientists have discovered GoPros, and so you strap on a GoPro on your shoulder, on your head, you're working on the back deck of the ship collecting things, and you want to go back and get some data that you might have missed, and you've got your GoPro video as a recording of that. We do standard laboratory data analysis where we've got data books, we're collecting information, but lots of different ways to collect data.
So what inspired you to research climate change, and when did your passion for it start?
The passion for my work in Antarctica started as a graduate student when I felt somebody tapping me on the shoulder in my lab one day, and I turned around, it was my major professor, and he said, "James," it's very formal, "James, I have a grant from the National Science Foundation, and there's room for one student to come, and I would like you to be that student." And so I went off to Antarctica with this professor for 3 months. He's a wonderful professor, scholar, amazing guy. We came back and we published 10 papers from our research for 3 months in Antarctica, and then that just set everything in motion. My interest in climate change came about when I reached Palmer Station, which was in the thick of these very rapid changes, and it was just impossible not to see what was going on. And that's what stimulated me to get involved in climate research.
So how can we stop the ice shelves from separating?
Well, really, to get at these big questions about slowing things down, you're talking about regulating the CO2 release into the atmosphere and slowing down the amount of global warming that's going on. There's nothing physical that we could do in Antarctica per se to slow that kind of process. It's more of a global process. So it's a big, big global issue that has to be addressed, I believe, in a multinational way.
So you talked about why you wanted to research climate change specifically, but what made you want to go into science as a young person?
It always gets back to that teacher. So I actually started at UC Santa Cruz as a literature major. because and this wasn't because I necessarily liked literature as much as I loved my high school literature teacher. And he was so fantastic, and he let me sort of do papers on the side that I got interested. I got interested in writing. And the same thing happened when I went to UC Santa Cruz. I took a course in marine biology the first semester, and there was a professor that I could just see the excitement in his eyes. And I got to know him, and he said, you need to go off to this marine lab and spend a semester there. They've got this great program in the UC California system, and students will be there from UCLA and Berkeley and all these different campuses, and the 20 of you will have this experience together for a semester, and you'll do research, you'll learn how to do. And I took that course, and it was clear to me then I wanted to be a marine biologist. So I really encourage all of you students to get involved in research in college, right when you're an undergrad. If you've got any interest in that area, don't wait to become a senior. Just go knock on a professor's door. Get involved. Yeah.
I'm a little bit curious about how you manage your family and being in Antarctica.
Sure.
It's not like they can settle there with you.
No, they've been there. They came on the cruise and saw where Dad worked at the station. I've got 2 children and my wife. What I would do as far as family life is I would restrict my stay to no more than 2 months. We're still married, so I think that worked. Communications have gotten better. If you read my book, you'll see that the first communications I had with my wife, who was my fiance at that time, was by Western Union telegram at $4 a word, which for a graduate student was a fortune. So she got about 6 words over 2 or 3 months. Now, when I get to the ice, you know what they hand me? They hand me an internet phone that looks for all practical purposes like a cell phone. I can hike up on the glacier miles from the station, sit down on top of the glacier all by myself, and call my family, and it's like they're sitting right next to me. It's amazing. So this communication explosion, this development, its ontogeny has really helped with that separation. But it's been a struggle, but it's been workable. Yeah.
So we're going to finish up, and I just wanted to, on behalf of Harker, we wanted to thank you for speaking.
Thank you very much.